right, let's fill in the solutions for this application exercise. So I'm doing this on the RStudio Pro server. So the first thing you're going to want to make sure you do is update your R version. So the default is R version 3.6.0, but to use the Tidy Models package, our IT folks have actually installed this on 3.6.2. So you're going to want to click on that version to make sure that you have that. And you don't need to save your R data, so you can say don't save. So make sure you've switched to that, and then go ahead and upload your Tidy Models starter RMD file. You can get that. Link from the from Canvas or on our website. And so I'm going to go ahead and run this here to get our packages loaded. And then let's go to our first question. So, and of course you'll want to update your author. Mine's already my name, but you'll want to make that your own. So write a pipe that creates a model that uses LM to fit a linear regression using Tidy Models. Save it as LM spec and look at this object. What does it return? So I'm going to call this thing LM_spec. And because I'm fitting a linear regression, I'm going to use the linear reg function. And I'm going to pipe that to the set engine function, and I'm going to set my engine as LM. So let's run that. And if we want to take a look at that object, we can run this LM spec here. And we can see the output. It says linear regression model specification, computational engine LM. So I'm going to go ahead and knit my results to make sure I save it. And there we go. It's got that output right there. Looks like it's working. Perfect. So now let's close that. And now this next part says fit the model from slide 13. So let's pull up slide 13. So I'm going to go to our website, STA363. f20.netlify.app. You can also go to bit.ly, STA363, bit.ly/STA363 F20. There we go. And I'm going to click on syllabus. I'm going to scroll down to today's lecture. So Introduction to the Tidy Models Part 1. We've got slides here, and we want to look at slide 13. So here we have it. So we have to fit the model, LM fit. We want to fit using this LM spec, miles per gallon, tilde horsepower, our data equals auto, and then we want to go ahead and look at that. And we want to compare that to the LM model. So let's go ahead and do that. So LM fit equals, we're going to set this, assign this. We're going to use the fit function. The first argument is going to be LM spec, the linear model specification that we set up here. And then the second is going to be the model that we're fitting, miles per gallon, using horsepower to predict miles per gallon. And our data is going to be the auto data set. This comes from the ISLR package. Let's do this so we can take a look at the output. All right, so this gives us a parsnip model. It tells us the LM function that's being run underneath because of the engine that we've set. And it tells us the intercept and the beta coefficient. So let's try to run the same thing using LM. So MPG tilde horsepower, data equals auto. So the results look exactly the same here. We've got the LM function that's run here, and we've got the coefficients, 39.9, same here, and negative 1.578, or negative 0.1578, negative 0.1578. So yes, it gives the same result. So let's knit this. All right. And that looks good. Okay, so the next part says, copy the code below, fill in the blanks to fit a model on the training data, then calculate the test root mean squared error. So the first thing we need to do is change this auto split. We want to create a split. I'm going to get rid of this eval equals false because eventually I'm going to want to evaluate this when I run my when I run my model, you'll notice it puts a whole bunch of little X's because everywhere there's a dash, that's not real R code. So RStudio is recognizing that that didn't work. I'm also going to go ahead and label this chunk. I'm going to call this split. Okay, so auto split. I'm going to use the initial split function. And I'm going to use the auto data set. I'm going to split this so that the proportion is 50-50. And now I'm going to pull out the training data of this auto split object. And then I'm going to pull out the testing data of auto split. Let's just run those first 3 parts. So you'll notice I have this set seed. As I mentioned in the slides, you want to use set seed because that makes sure you get the same answer every time. Otherwise, every time I do this split, I'll get a slightly different set in my training and testing data. And so now I can look at my auto split object, and this tells me I have 196 in training and 196 in testing. And I can look at my auto train, and I see I've got my auto data set here. And this is going to have, let's see how many are in. Let's look at the number of rows in auto train. Got 196 rows, so that worked. And then we can look at the same in auto test, also 196, so it looks like that worked. Okay, so now we're going to do LM fit. We're going to fit this model based on the specification that we've set. But we want to fit it just to our training data. And so I'm going to fit this to auto train. And then I'm going to take this fit, and I'm going to pipe it into the predict function. Now, what do you think I'm going to put in the new data? So because I want to calculate the test error, I'm going to put auto test here in this new data, and I'm going to bind the auto test data. I'm going to bind those columns. So now this MPG pred, this MPG predicted values, if I look at that, it's got this predicted column here, but I just have 196 observations that I have these predicted values for, and these are my 196 testing observations, the ones that the data was not trained on. And now I can calculate the root mean squared error on this MPG pred data frame. The truth is going to be MPG, that's my miles per gallon column, and the estimate is going to be dot pred. So I see here that my test root mean squared error is 4.83. So there you have it. All right, so now I want to edit the code to get 5-fold cross-validation. Oh, you know what? Before we do that, let's go ahead and run this real quick. Let's knit it so that we can save our result. This is just saying that it wanted to create a pop-up, and I'm going to say try again so that I can get that pop-up to see my output. Okay, looks like it worked, 4.84. Oh, and I'm seeing that I actually accidentally skipped one here. So this, I was supposed to edit the code to add the original data to the predicted data. So how do we do that? Well, the original data is going to be added with the bind calls function. And so bind calls will bind the columns from the data frame with the columns from the predict. Let me just run this part, just the predict with the new data equals auto. And just as a reminder, this code here, because I'm using auto as the new data, and in this case, this LM fit object up here was fit on just my full auto data. When I run it down here, I'm going to end up getting the training error if I were to run something like root mean squared error. Okay, so let's run just this part to see what this outputs. So this outputs a data frame with just one column called dot pred. So if I just run LM fit and I pipe that to the predict function, it's going to create a data frame with one column, dot pred. And so to add that column to the data frame that was used to generate it, I have to use the bind calls. And so that will bind the columns together from this data frame and the auto data frame. And so if I run this, I end up with this MPG pred that comes from this auto data that has all 392, because in this case, we're using the full data set. We haven't done the split yet. And we've got our full data plus this new predicted column. Okay, so I'm gonna get rid of this eval equals false here, and I'm gonna label this chunk predicted. So let's go ahead and knit that. All right, so that looks pretty good. Now we just have to do this last question. So this last question is asking us to edit the code to do 5-fold cross-validation for the following model. We want to have horsepower and horsepower squared. So there's a couple ways to do this in R, but the way that I'm going to do it, well, first let's create our cross-validation object. And so because we're doing 5-fold cross-validation, we're going to set v equal to 5. We're using the auto data frame here. And so if we look at this auto CV, it's this 5-fold cross-validation object. And then because we're doing cross-validations, instead of using the fit function, I'm going to use fit resamples. I've got my LM spec. And now this is where I'm going to put in the formula. So this is going to look similar to the other ones, except instead of just having horsepower, I now want to have horsepower squared. So one way to do this is to use this I function. If you want to learn about what that is, basically it changes the class of object to indicate that it should be treated as is. And so this is in a formula, basically it's a way to be able to square it. There's another way that we could do this is by using the poly function. I'll show you that in just a second, but let's do it like this first. So my resamples, my object is going to be this auto underscore CV, this cross-validation object that I created up here. And so let's run that. And so it's creating this, it's creating these 5 predictions, and it says prediction from rank deficit fit might be misleading. So basically saying that we don't really have a ton of data to be fitting these models because we're fitting them on a little bit smaller data sets, and so it's saying that it's possible this might end up with a misleading result. And so when we collect the metrics here, the root mean squared error for this cross-validation is 4.87 with a standard error of 0.38. And then down here I've got R squared. So this RSQ, this is R squared, and you might remember R squared is basically, it helps account for the percent of variation that's accounted for by the predictors. And so in this case, it's 0.6. And so 60% of the variation in miles per gallon is accounted for by horsepower plus horsepower squared. So I'm just going to show you now down here a couple different ways and to be able to include this miles, this squared term. And so I'm going to do it using just the fit function because it's easier to be able to show it that way, because then you don't have to worry about kind of the different, digging into the different pieces of cross-validation. But if I was, so the way that I did it was horsepower plus horsepower squared. I'm going to set my data to equal to auto. So you'll notice here, oh, hold on. There we go. Oh, you know what? Maybe this needs to be, let me fix this real quick. This needs to be on the inside. There's a typo in my code. I want to make sure that we are all clear about this. So the way that you do this is that you've used the I function, but the squared should go on the inside. And let's run that real quick. So that was causing our problem before when we were seeing that it was rank deficit. And so this actually fixes that problem. And now you'll notice the mean is 4.36, which is a little bit closer to what we would have expected, that average cross-validation error is going to be closer. It's going to be a little bit smaller than what we got here when we did the validation set approach. Okay, so back to this. So this is one way to show it where you use this I function. Another way to do this, and let's pull out the predicted values here so we can see what those are. So those are, here, I'm going to save these as predicted with I. Okay, I'm going to show you another way to do this. Is going to be using the poly function. And so this fits a polynomial. And so I want to use horsepower, and I want to use a second degree polynomial. Now, when you look at this, if you look at the actual coefficients, they're going to be different. So here the coefficients are 23, negative 120, and 44. Whereas here the coefficients are 56, negative 0.4, and 0.0012. So these give different coefficients. But when I run the predict function, let's compare predicted poly to predicted I. So what I'm going to do is I'm going to compare this pred column and predicted poly. Actually, let's bind these columns together. I think that's a nice way to do it. So we're going to bind the columns of predicted I and predicted poly. And then I'm going to create a new variable called diff, which is going to be predicted I minus predicted poly to see how different these predicted values are. Oops, this should be dot pred. Hold on, let's run this first. So we're binding these columns. We end up with dot pred, which is, this is from the I, and dot pred 1, which comes from the poly one. So we're going to do dot pred minus dot pred 1 to get a diff column. And if we summarize across the mean of this difference, it's this really, really, really small number. We could round this to even 12 decimal points and we'll get 0. So basically there's no difference between these two. So what that's telling us is that this poly and running your model like this, where you have the first variable and the second variable squared wrapped in an I function, these will give you the same predicted values, but they'll give you different beta coefficients. And that's because the poly function, it is doing a polynomial, but it's centering those values first. And it's actually doing a little more than just that. You can look at what it does if you run question mark poly. You can look in the help file. And so it's returning or evaluating orthogonal polynomials. And so orthogonal polynomials means that those are basically the polynomials that are created are independent from one another. And so that's going to give you a slightly different beta coefficient, but it's going to give you the same predicted value. Okay. So what would happen if instead of using the I function, I tried to just run this like this, horsepower plus horsepower squared? So it looks like it just doesn't do anything. So it doesn't add in that second part. And so that's why you need to have this I wrapped around it to basically say you want to evaluate that function exactly as stated. And I want to reiterate, one time when I had initially typed this in, I had accidentally put the squared part on the outside of the I, which is not what you want to do. You want the full expression to be inside the I. So you want horsepower squared to be like that. Okay, there you have it. So that's our application exercise. I'm going to delete this extra part down here where we've just been working on stuff. I'm going to set this to eval equals true, or just delete the eval equals false. I'm going to call this chunk cross validation. And I'm going to knit so we get save our final results. And there we have our full, all of our answers for application exercise 3. So now you'll take this and you'll download this HTML file, and then you can go ahead and upload it to turn it in.